Good morning, students. Today we are going to take the class number 6 for the final BSc paper 5. The paper name is Ring Theory and Vector Calculus for the AKNU Aditya Nanya University for the academic year 2020-2021, 5th semester, Unit 1, Rings 1, class number 6. Now we learn the definition of subring. Previously we learned definitions of ring, abelian ring, integral domain, field, division ring, field, like that, and also the characteristic of a ring and nilpotent element definition. Now we are going to the another definition, that is subring. A non-empty set subset S of a ring R plus dot, operations are plus and dot, is said to be a non-empty set subset S of a ring R with respect to two binary operations plus and dot is called subring of R if S is itself is a, again I am repeating the definition of subring, a non-empty subset S of a ring R plus dot with respect to two binary operations plus comma dot is called subring of R if S is itself is a ring. That means if we take any non-empty subset in a ring R is said to be subring if its S is itself is a ring. The operations are same as taken on R. If R is taken the operations plus comma dot, then S is also, on S is also we are taking plus comma dot. By using this definition, now we are going to discuss another theorem, that is theorem number 8. The statement is, this is very important theorem, if S is non-empty subset of ring R plus dot, then S is subring of R if and only if A minus B belongs to S, comma, A dot B belongs to S for all A comma B belongs to S. Okay, right. Here is if and only if is there, IFF. That means if and only if means necessary and sufficient conditions. We have to prove necessary condition and sufficient condition. The common portion for the two conditions is S is non-empty subset of ring R plus dot. So students, now we are taking that what is given, S is given, S is non-empty subset of ring R. I have written here given S is non-empty subset of ring R. Now I am taking necessary condition. What is necessary condition? If we take the LHS part, that is if we take that S is subring of R, we have to prove these two bits. Those are A minus B belongs to S, A dot B belongs to S, when for all A comma B belongs to S. For that I am taking left hand side S is subring of R and we want to prove these two. Okay, right. What I am writing is, suppose S plus dot is subring of ring R plus dot. If you observe that the binary operation plus and dot are on R, the same binary operations are there on S also. Okay, right. Next, we want to prove that A minus B belongs to S and A dot B belongs to S for all A comma B belongs to S. We have to prove these two conditions. For that, we have to take two elements. For any two elements, A comma B belongs to S. B belongs to S. What is S? S is subring. Subring means itself is a ring. Itself is a ring means it is satisfying S plus abelian group, S dot semi group, distributive laws, all these conditions are satisfying in this S. So S plus abelian group means abelian group. In abelian group we have 5 laws. What are they? Closure, associative, identity, inverse and abelian. By the inverse law, B belongs to S means minus B also belongs to S. Here A belongs to S, minus B belongs to S. Again, by using the closure law on S, using the closure law on S, A plus minus B belongs to S. Plus into minus, minus. A minus B belongs to S. A comma B belongs to S we have taken, and we shown A minus B belongs to S. That is the first bit was clear. And the second bit, A dot B belongs to S. Okay, we have taken A comma B belongs to S. What is S? S is subring. Subring means ring. Ring means S plus is abelian group. S dot is semi-group. Semi-group means closure law, associative laws are satisfying in S with respect to multiplication. So by closure law in S, with respect to multiplication, for A comma B belongs to S, A dot B is also belongs to S, which is the second condition proven. Both these two conditions were proven by us by taking for A comma B belongs to R. We have proved A minus B belongs to S and A dot B belongs to S. Therefore, the necessary condition was proved. Now we are going to the second condition, that is sufficient condition. What is sufficient condition? We take the RHS part and we prove the LHS part. What we have to take in the RHS part? A minus B belongs to S, comma A dot B belongs to S for all A comma B belongs to S. If you observe that in the sufficient condition, suppose A minus B belongs to S, A dot B belongs to S for all A comma B belongs to S is taken. Now we prove that S plus dot is subring of R plus dot. For that, S is subring of R, we have to prove that S is itself is a ring. S is itself is a ring means we have to prove that S plus is abelian group, S dot is semi-group, and distributive laws holds in S. We have to prove these three conditions. First of all, we prove that S plus is abelian group. Okay, right? We prove that S plus is abelian group. For that one, first of all, I am taking that A comma A belongs to S. Our supposition is this. What is that? A minus B belongs to S, AB belongs to S when A comma B belongs to S. Okay, right. I am taking here A comma A belongs to S. By using our supposition, for A comma B belongs to S, A minus B belongs to S. For A comma A belongs to S, A minus A belongs to S. By our supposition, A minus A means 0. 0 belongs to S. What is 0? Additive identity. Additive identity is in S. Is it right? That means identity exists in S. Okay, right. Now I am taking in the second bit for an element A belongs to S. Since we got that 0 belongs to S, now again by the supposition A comma 0 or 0 comma A belongs to S means 0 minus A belongs to S. Whereas A comma B belongs to S means A minus B belongs to S. By using this supposition, 0 comma A belongs to S implies 0 minus A belongs to S. 0 minus A means minus A belongs to S. For A belongs to S, minus A belongs to S. What is minus A? Minus A is additive inverse of A. We know that. This additive inverse is in S. That means additive inverse exists in S. That means inverse exists in S. Identity exists in S. Now inverse exists in S. Now I am taking two elements A comma B belongs to S. Since B belongs to S means minus B belongs to S by this second bit. What we proven that? We have taken A belongs to S. We proven that minus A belongs to S. Similarly, by this second bit, if B belongs to S, minus B belongs to S. A is written as it is in the next step. And B belongs to S means minus B belongs to S by second bit. Okay, right. A belongs to S, minus B belongs to S. A minus of minus B belongs to S. This is by the supposition, because in the supposition A comma B, are you following the cursor, students? A comma B belongs to S gives A minus B belongs to S. That's why A comma minus belongs to S, the same condition, A minus B belongs to S. A as it is, minus into minus plus B belongs to S. For A comma B belongs to S, we proven that A plus B belongs to S. That means closure law exists in S with respect to operation plus. Now we are going to the fourth condition and fifth condition. Those are associative and abelian laws. For that, we are taking three elements for A, comma, B, comma, C belongs to S. We know that S is subset of R. What is that meaning? All the elements of S are in R. So A, B, C are in S. That means A, B, C are in R, because S is subset of R means all the elements, all these three elements in S are also in R. Okay, right. But R is ring. What is that? R is ring. Given that, can you follow the cursor in the theorem number 8 statement? R is ring. So I am using that definition. That means the given thing, R is ring. R is ring means R plus C is group, abelian group. Abelian group means it satisfies closure, associative, identity, inverse, and abelian laws. Now A, B, C are elements of R. That means these three elements satisfies associative, the second one, and the last one abelian also. I am writing this associative law and this abelian law. What is associative? A plus B plus C is equal to A plus B plus C. Now what is abelian? A plus B is equal to B plus A. These two were proven for the elements A, comma, B, comma, C in S. That means associative and abelian laws proven for the elements in S. So associative and abelian laws exist in S. What we proven previously? Identity exists in S, inverse exists in S, closure exists in S, associative and abelian laws exist in S. That means the five laws are satisfying with respect to the operation plus. So we say that S plus is abelian group. Now we prove that S dot is semi group, and also we prove that distributive laws. Before going to prove this, in our supposition, S dot semi group means we have to prove two conditions, that is closure and associative. What are the two laws? Closure and associative. With respect to the operation here, what is? Dot. In our supposition, we have that if you observe that A, comma, B belongs to S gives A dot B belongs to S. We have taken the supposition. Kindly observe it. The cursor top black line, first black line of this page. The cursor is moving. A, comma, B belongs to S gives A dot B belongs to S. What is this? This is closure law with respect to multiplication. Is it right? So we don't want to prove this closure law because we have already supposed this is a closure law exists in S. So in that semi group, we want to prove that S dot semi group closure law exists. By our supposition, A dot B belongs to S means closure law with respect to multiplication exists in S. Okay, right. What we have proven that in that semi group, the second law is there. The first law is closure law existed, and the second one is associative law with respect to multiplication, and after that we want to prove distributive laws. Okay, right. For that one, I am taking that 0, comma, A, comma, B, comma, C belongs to S. Because S is subset of R, means all the elements of S are in R. That means all these four elements of S are also in R. So 0, comma, A, comma, B, comma, C belongs to R. 0 is not needed here. We can remove A, comma, B, comma, C in R. But R is ring. R ring means R dot semi group distributive laws holds. That means with respect to dot associative law is already exists for the elements of R. ABC are in R means associative with respect to multiplication, that is A dot B dot C is equal to A dot B dot C was exist, and the distributive laws also exist. That means A dot B plus C is equal to A dot B plus A dot C, and the second one is right distributive law is B plus C dot A is equal to B dot A plus C dot A. That means what are the elements A, B, C? In these elements are in S. For the three elements in S, we have proven that associative and distributive laws were exist in S. That means S dot is semi group and also distributive laws holds in S. Therefore, what we have proven that before that we have proven that S plus abelian group S dot semi group and distributive holds. That means that S plus dot is ring. So, but S is in R. But S is subset of R. S is ring, R is ring. S is called subring of R. So S is called subring of R. So the sufficient condition is also proven, so the theorem was over.